Hello, I'm Leo Godin, and I am the creator of LDL Learn Deep Learning. This presentation is for the Data Science Practicum 1 for Regis University. LDL is a deep learning framework for learning about neural networks. Now, it's not just a neural network or a framework for accomplishing production work. Instead, it's for people who want to dig deeper and create a neural network from scratch. In fact, it's created with just Python, NumPy, and Pandas. And NumPy is providing the ability to perform matrix multiplication, and Pandas stores and plots results, and that's about it. Everything else is plain Python. And even though it's intended to be in a learning environment where a data scientist would create their network from scratch, it comes pre-configured so that it can be used right away, and only portions of the network need to be coded from scratch. In fact, starting out, none of it does, but over time, in order to learn better, the data scientists would code their own functions. And we'll get into how that works in the next slide or two. So you might ask, why would someone create a new deep learning framework when there's so many good ones out there, and much better ones, frankly? Well, it goes back to what I said earlier. The purpose of LDL isn't to create a production network, neural network. It's to learn about neural networks. It's to learn the steps, all the little pieces that need to come together in order to train and predict. It also allows incremental development. So creating a neural network from scratch can be daunting. There's a lot involved, and it's difficult to learn or to tell if you're doing a good job until you're done. You have to have all of the pieces together in order to test whether you've done a good job. With LDL, you don't have to code the whole network from scratch. You can start with small portions, for instance, the activation functions or the cost function, and leave everything else the way it is, so that when you implement a small part, you'll be able to see results in a working neural network. More importantly, this implements my learn, do, learn philosophy, which means learn something, do something practical, learn some more, rinse and repeat. In fact, I usually call this learn, do, learn, teach. So the idea is you would learn something, do something practical, maybe learn some more, and then teach it to someone else. LDL fits in this framework because it provides an environment to practice and to do some practical exercises. Now, like I said, LDL comes out of the box ready to train and predict a neural network. But in order to learn, you want to create your own functions and replace some of the functions that come with LDL. So, for instance, you see here in the image, I've created a new ReLU activation function. This one's actually a very poor one because it's not vectorized, but we'll get to that in a little bit. And in order to use this activation function instead of the one that comes with LDL, we simply assign this function to activation fun of the network. I've made it as simple as possible. There's no getters or setters. It's simply your network dot whatever function it is and what your new function is going to be. Very lightweight API this way. The documentation is in read the doc style, and it shows you which functions can be overridden. Now, LDL is complete and it works and all the tests have passed, but we still need to do some analysis for this practicum. So in this case, I'm using the MNIST data set, which is a data set of 60,000 handwritten digits for between 0 and 9. They use college students and people who were out of college to try to get different perspectives and different handwriting styles. Now, each row in the data represents the pixels from a 28 by 28 matrix. And if you look at these numbers, you'll see where there's something that's really dark, that would be an intense value, somewhere near 255. Something that's empty would be 0, and something that's kind of light, like the 7 over here, maybe that would be a 155 or something like that. Now what I want to do is classify 10,000 test digits. So out of the 60,000, I'll take 10,000 out for testing and see how good we can get. The world-class classifiers today get 99.99% or something like that. They're near 100%, and I would not expect LDL to get close to that, but we should be able to get well into the 90s. Now let's look at some exploratory analysis. First thing we have to look at is the weights and biases. So in a neural network, you have to initialize the weights and the biases, and that could be really tricky. In fact, it was really tricky for me, and I got to a point where I thought I might not be able to complete this project. What you'll see here are 4 examples of 4 different ways I initialized the weights, and just 10 epochs to see how they behaved. You'll see that random initialization between 0 and 1, -0.25 and 0.25, and even -0.5 to 0.5, all fail pretty quickly. In this case, you see a test cost of exactly 0.5 and an error rate of 90%. What that means is, since there are 10 digits, we're guessing 10% of the time, and it's not giving us any results. Over here, this -5 to 0.5, it changes a little bit. We do see an error that starts high and goes low, but we should see more dramatic changes even in the first 10 or 20 epochs. What I found was there is an optimal way to initialize the weights and biases, particularly for the ReLU activation function. He and al. Performed some experiments, and they found that the weights should be initialized in a range that depends on the number of input and output neurons to those weights. And when I use the He method, you see that I get a cost that's decreasing nicely, and I also see a test error that's decreasing nicely, right, from 91 to 90 down to 74%. This looks like it's working. So we'll use the He method of initializing these as we move forward. And I've created a function in LDL that you can pass in the network topology, and it will create the weights for you. Next, we have to look at architecture. Now, I decided on a 3-layer network with 1 input layer, an output layer, and 1 hidden layer. And here we're seeing results of training with the He initialization of weights and bias, a learning rate of 2, and an increasing number of neurons in the middle layer, in the hidden layer. And we'll see here that when we get to 784 by 100 by 10, which means there's 784 input neurons representing each pixel in the digit, 100 neurons in the hidden layer, and 10 neurons in the output layer, which would represent 0 through 9 for the digits. The 100 neuron works best. In fact, you see it quickly going down, getting well below 10% error rate. We see some strangeness when we only have 10 in the hidden layer. You see it bounce around early and then kind of just flatten, and it actually increases the test error, which is interesting. Over here with 50, we don't get an increased test error, but we actually don't get great results, and I'm not sure why that is. It doesn't look like it's a matter of just increasing the neurons, but 100 neurons seems to work better than 50. But yet 25 worked better than 50 as well. Now we want to look at the learning rate. The learning rate sets the magnitude of changes in each epoch. And here I ran 10,000 epochs using the weights and biases from earlier and the 100 neurons in the hidden layer. And we went from 0.03 all the way to 0.3, 0.2, and 0.1. In my testing, I probably tested 15 different learning rates, but these were the most interesting and showed the best picture, so I included them here. In the end, we find that a learning rate of 0.3 provides the best results. And we'll see that down here. After 10,000 epochs, we had an error rate of just over 5%, which isn't bad. Not great, but it's not bad. But you'll also see that over time, our costs have increased and the learning rate has actually increased. Matter of fact, if we look a little closer at the output from each epoch, you'll see that we get down to below 3%, and then as the epochs increase, our cost is getting higher, which means we've overtrained. And our model isn't going to generalize well. So if we cap it off around 4,700, we'll be below, or maybe 4,800, we'll be below 3% error, which would give us a 97% accuracy, which is really good for a custom-built network with no convolution layers or anything like that. Just a note on vectorization. So in one test, I implemented the ReLU activation function, and I ran 10 epochs, and I didn't use vectorization, so I used for loops. As a matter of fact, I showed you that a few slides up. Now with for loops, it took 99 seconds to run 10 epochs, which means almost 10 seconds an epoch, which would be almost impossible to train. With a vectorized function that does the same exact thing using matrix multiplication, or matrix operations, finished in 7 seconds. So we're an order of magnitude faster with vectorization, and that's just one function. Now imagine all the other functions as well. Vectorization is essential to being able to train your network in some reasonable amount of time. So our results. Well, we achieved 97.04% accuracy using 4,700 epochs. And a learning rate of 0.3. More importantly, I learned the ins and outs of neural networks, and others can use this work to help them learn and practice. I learned some lessons. Details are critical. The derivative of the quadratic cost function includes your predicted minus the actual, whereas your cost function itself is the actual minus predicted. When I started out, my cost was rising instead of falling. Building networks is an art. There are things you can do to ensure they work well or to hope they work well, but many times you just have to use trial and error, something they call grid search. Beginners need troubleshooting tools more than fancy visualizations. Once I started using LDL, I realized I needed to show more troubleshooting than try to focus on a visualization that shows the network. So I chose to go with better troubleshooting tools. And when you're taking a big project, you want to eat the elephant one bite at a time. Break everything down into components, test the components individually, and things are a lot easier. So in conclusion, LDL is a framework that allows data scientists to incrementally build a neural network from scratch. It provides default functionality, so each step along the way you're rewarded with a fully functioning network, even if you've only created one function. We achieved 97.04% accuracy on the MNIST data set, and most of all, I learned how neural networks backpropagation and gradient descent work well enough to implement them, and implement them in a vectorized fashion. And I think that's the real reward I got from this project. Thank you.